All right, so we're going to finish out lesson 4 by looking at a few more examples. And this time, I want us to take a look at some examples that actually involve absolute value. If we think about what the absolute value of x looks like, we know that this graph is going to look like this. And hopefully we could look at this limit and just simply know that if I substitute, well, let me rephrase that. Knowing that this graph of the absolute value looks like this V, we could, by inspection, looking at the graph, know that the y value that this function approaches as x approaches 0 from the left and the right is equal to 0, based on the fact that we know what the absolute value function looks like. But let's look ahead at this function here. This function, involves absolute value, but it's also written in the form of a rational function. So this particular function might not behave like this function. The only thing that we know that these two have in common is that they both involve absolute value. If I directly substitute 4 for x here, I get 0. If I substitute 4 here and subtract 4, I get the absolute value of 0, which is 0. So on this, I know I'm going to have to do more work. Well, what I'd like to do is I want us to see or talk about, even though we know what the limit of this function is based on the fact that we know the graph is this V shape and it's the mom and daddy graph for the absolute value function, I want us to think of this from a different perspective. If you think about this function, we could think of this in terms of a piecewise function. This particular graph, I'm going to cover this up. This particular function could be defined as a piecewise function where we have an equation for this piece and we have a little equation for this piece. Clearly, these two branches of this graph are different and then can be defined as two separate pieces. So in other words, I could take my function or my limit and I could actually write this as the limit as x approaches 0 of f of x, which equals, now this piece, what would the equation for this piece be? Well, that's just your mom and daddy line that has a negative slope. So this piece would be defined as the opposite of x for the x's that are less than 0. This red piece is defined as, and it's just the mom and daddy graph with a positive slope. So the equation for it would be positive x, and you could leave the positive off. And this piece is defined for the x's that are greater than 0. Now, the good thing here is that you get to choose, when writing a piecewise function, you can choose which of these pieces gets to include 0. So since I've got my red pen in my hand, I'm going to let this piece be the piece that includes 0. Okay, so if this is the case, how do we go about finding the limit of a piecewise function? Well, if you recall, to find the limit of a function, especially when it's a piecewise function, you have to find the limit of the function as x approaches 0 from the left. Well, what is the function, or how is the function defined for the x's that are less than 0? Well, that's negative x. Well, substitute 0 for x, and you get negative negative 0, which is simply 0. Now that's only part of it. If we want to find the limit as x approaches 0 from the right, that would be for the red piece. And the red piece is defined as positive x, and if I substitute 0 for this x, I get plus 0. And the nice thing about 0 is that it's neither positive or negative. So the left-hand limit is 0, the right-hand limit is 0. So the limit, I'll just squeeze it in, the limit of the absolute value of x as x approaches 0 is equal to 0. And that's what we said from the very beginning. But we don't know what this function looks like. And could we graph it? Yes, but we're not going to, because we have to be able to find a limit as x algebraically and without a calculator of any kind. So when you substitute your 4, we've already talked about how we would get 0 over 0. So you might say, okay, well, how do you know what technique to use? This is a rational function, but what I see is the fact that it ends up having an absolute value. So at x equals 4, that's where something is going to happen with the graph of this function. So I can rewrite this function as a piecewise function. When you have something that involves absolute value, then you want to rewrite it as a piecewise function. All right, so how do we do that? Well, you remember how over here, this is very simple, but remember how we took this absolute value function and we removed the absolute value and made one of the x's negative and one of the x's positive, okay? We're going to do the same thing here. So my function I'm going to have is the limit as x approaches 4 of the function. I will remove the absolute value of x minus 4. One of these will be negative, and I'll have x minus 4 over x minus 4. And that's defined for the x's that are, because this is negative, this will be for the x's that are less than 4. And then I will also rewrite this expression without the absolute value for the positive version of x minus 4 over x minus 4. And this piece will be defined for the x's that are greater than 4. And you can determine which of these that you want to include for. So I just do the bottom one. So now to determine the limit, this is a piecewise function, so we have to substitute 4 we have to find a left-hand limit and a right-hand limit. Well, here's the nice thing about this. This is going to be the limit as x approaches 4. This expression can be simplified. Well, what is x minus 4 over x minus 4 going to do? Those are going to cancel, and I'm left with negative 1 for the x's that are less than 4. And the x minus 4's cancel here, and you're left with positive 1 for the x's that are greater than or equal to 4. So the left-hand limit, the limit as x approaches 4 from the left of negative 1 equals negative 1. The limit as x approaches 4 from the right of positive 1 is positive 1. And since the left-hand limit and the right-hand limit are not the same, then the limit as x approaches 4 of x minus 4 over the absolute value of x minus 4 does not exist. And it does not exist because the left-hand limit and the right-hand limit are not the same. So, out of curiosity, I'm curious if we could figure out what this graph looks like based on this information right here. If we look at this from a piecewise function, this expression and this expression, these two things are equivalent. They definitely don't look the same, but they are equivalent. So if the limit as x approaches 4 from the left is -1, then my graph, the graph of this, where's 4? 4 will be over here. Then what this is saying is that the y values are always 1. This is a constant function for the x's that are less than 4. And so the y value is at -1. So here's -1. I will have an open circle at -4. That's what this looks like. And then as x approaches 4 from the right, this is a constant function of 1. And because I've included it, I will have a closed circle. And that's what the graph looks like. So this particular function does not look, well, there are some similarities between these two graphs, but notice that this graph does not involve the absolute value function. It is not, the two pieces here are not connected to make that V shape. So that's an interesting function, but anytime you need to find a limit that involves an absolute value, if substitution gives you 0 over 0, the indeterminate form, then rewrite the function as a piecewise function. And then find the limit, find the left-hand limit and find the right-hand limit. If they're the same, that's the limit. But if they are not the same, then the limit does not exist. Okay? All right, so that kind of wraps up some of our techniques and tools that can be used algebraically. For right now, I want us to take our calculator and I want us to look at a couple of graphs and identify the limit. And in doing so, there's just a couple right now that we need to memorize, okay? So, the limit of sine of x over x as x approaches 0. If I do the substitution, sine of 0 over 0. Well, think about sine of 0. Sine of 0 is 0 over 0. So that would mean do some more work. Well, right now, this I would actually save for later until we get to that L'Hopital's rule. But for now, there's a couple of limits I want us just to memorize. And this is going to be one of them. So let's graph this. Let's see if we can graph this function and identify what the limit is as x approaches 0. So go to y equals. Let's clear that out. And I will type in sine of x, and I will close x. I'm going to make sure my mode, before I do anything else, is in radians. And now I'll go back to y equals, and then divide by x. So now I'm going to zoom trig, so it's zoom 7, and here comes the graph. And so remember, graphically, if we want to find the limit as x approaches 0, we're looking at it from both the left side and right side of 0. So the graph appears to, the y values appear to approach 1 from each side. So the limit of sine of x over x as x approaches 0 is 1. Now, if that were x approaches something else, you would have a different value. But this is This is one that I need for you to, for now, just to remember. The limit of x, as x approaches 0 of sine of x over x is going to equal 1. All right, and then there's another. Let's look at this one. If I substitute 0 for x here, I'm even going to use my circle information over here. Cosine of 0 is 1. 1 minus 1 is 0 over 0. So again, let's graph this and see what it looks like. So I'll go into y equals. I'll clear that out. I'll open my numerator with parentheses. I have cosine of x, close the x, subtract the 1, and close the numerator. And then divide by x. And let's graph. Yeah. So again, as x approaches 0 from the left and from the right, the y value is 0. So these are two that would be very helpful for you to know right now, just as to memorize. Just to memorize and know. Okay? Okay, so then let's look at a couple of examples that are in like multiple choice style, AP multiple choice style. So here we have, we want to find the limit as x approaches 0. If I substitute 0 for x, this 9 plus 0 is 9. The square root of 9 is 3. 3 minus 3 is 0 over 0. So just because you end up with 0 over 0, do not think that your answer is A. Remember, do more work. Do more work. So what would that work be? Well, remember what I said. When you have a rational function and it involves a radical, then you should think of rationalizing the, in this case, the numerator. So let's rationalize. That would mean I need to take or have the limit as x approaches 0 of 3 minus the square root of 9 plus x over x, and I want to multiply this by the conjugate of 3 minus 9 plus square root of 9 plus x. So that would be 3 plus the square root of 9 plus x over 3 plus the square root of 9 plus x. All right, so help me remember, how are we supposed to multiply these two expressions? Do I actually multiply the two numerators together? Do I actually multiply the two denominators together? All right, well, remember, when you have something like this, you want to multiply the conjugate pairs. The numerators are the conjugate pairs, so this is what I've got. The limit as x approaches 0, when I multiply, I have 9 minus, and this is where you have to be careful. When you multiply the square root of 9 plus x with the square root of 9 plus x, you're left with a binomial, 9 plus x. It's so very important that you put 9 plus x in parentheses, because when you multiplied negative square root of 9 plus x with positive square root of 9 plus x, you ended up with a negative. And so that negative has to apply to both of those. So in my denominator, though, I want to leave my x, and I'm going to multiply this by the sum of 3 plus the square root of 9 plus x. So remember, multiply the conjugate pairs, and don't physically multiply your the pairs that are not conjugates. So cleaning this up, I end up with the limit as x approaches 0. 9 minus 9 is 0, but my x becomes negative x over x times 3 plus the square root of 9 plus x. My x's will cancel, and I have the limit of negative 1 on top as x approaches 0 over 3 plus the square root of 9 plus 0. And so the 9 plus 0 is 9. Square root of 9 is 3. This is going to give me negative 1 over 6. So going back over here, D would be the answer. Okay. All right. And I have included yet another example that is a rational function that involves a radical. If you substitute 25 here, you get 25 minus 25 over 5 minus 5, and that is 0 over 0. So let's think about what we can do here. The limit as x approaches 25, I have x minus 25 over the square root of, not 5, but the square root of x minus 5. So we want to, this time, the radical's in the denominator, so let's rationalize the denominator. So when I rationalize the denominator, I get the square root of x plus 5 over the square root of x plus 5. And the rule and the instructions are the same. You want to multiply the conjugate pairs, but you want to not multiply or physically multiply the pairs that are not conjugates. So what in the world is that going to look like? Okay, so I've kind of got a mess here, and I'm sorry. Okay, so here's what I've got. I'm going to bring this down here. So here I have the limit as x approaches 25. My numerators are not conjugate pairs. This numerator is a binomial, so I'm going to write it in parentheses. I'm going to multiply that by the square root of x plus 5, and I will close that, over my denominators are conjugates, so I will actually multiply the conjugate pairs. X, square root of x times square root of x is x. These are conjugate pairs, so the middle terms will cancel. Negative 5 times positive 5 is negative 25, or minus 25. So now we have a factor of x minus 25 in the numerator. We have a factor of x minus 25 in the denominator. And now we end up with the limit as x approaches 25 of the square root of x plus 5. So now I can substitute square root of 25 plus 5, and that equals 10. So your answer to this would be 10. And I do apologize for lack of space. Y'all may have been able to write smaller, but. All right, so those are some examples of how we can use techniques to find limits algebraically. So now let's try to look at this. Let's look at a problem from an FRQ's perspective. Okay, so remember, an FRQ, a free response question, is going to have some information, and then it will have multiple parts to it. So it says, given a function, f of x equals x minus 8 over x squared minus 7x minus 8, find the following. Okay, so it wants us to find for what value or values of x is f, the function, not continuous. Well, okay, so what kind of function do we have? This is a rational function. So we need to determine what values of x, if any, make that denominator equal to 0. So I'm going to rewrite this first in factored form. So my f of x equals, I have x minus 8 my denominator will factor into, this is good, x minus 8 times x plus 1. And from this version, I know that this function will not be continuous at whatever x value makes the denominator 0. So, x equals 8 and x equals -1 are the values that make this function f not continuous. So, this is an FRQ. Answer the question. It says, for what value or values of x is f not continuous? F is not continuous at x equals 8 and x equals -1. All right? So now the question is, for part B, it says determine whether each value is removable or non-removable. Okay, and what we're talking about here, and I should have done a better job of writing this, but at each point of discontinuity, 8, -1, determine whether the values are removable or non-removable. Are the points of discontinuity removable or non-removable? Okay, well, how do you determine that? Well, this is a rational function. So remember, if x minus 8 is a factor that cancels, that means that there is a hole at x equals 8. And a hole is removable because remember, it looks like somebody has reached up to the graph and plucked a hole or plucked a point out of the graph. So x equals 8 is a removable discontinuity. Now let's talk about the leftover value that makes the denominator 0, which means the function is not continuous there. So remember that with a rational function where x, where you have a factor that cancels, you will have a hole. Whatever factor in the denominator does not cancel, you will have a vertical asymptote. So that would be non-removable. So here we have a hole, here we have a vertical asymptote. So at x equals -1 is a non-removable discontinuity. Okay? All right, and then a third part to this particular problem, FRQ problem, would be to find the limit of x minus 8 over x squared minus 7x minus 8 as x approaches 8. So a lot of the work has already been done. We've done a lot of the work that we need to do for this already. So what we need to do is we'll need to say that the limit as x approaches 8 of 1 over x plus 1 is going to equal, and I like to use arrows because this is just kind of telling the reader, hey, here is my thought process. You have to be careful about equals, but anyway, we'll talk about that a little bit more. But now I will substitute 1 over 8 plus 1, and that gives me 1/9. So at as the limit as x approaches 8, I have taken my factored version. My work is already here. I don't have to do it again here. As long as my work is shown in another part, then I can go ahead and write this as the limit as x approaches 8 of the reduced form 1 over x plus 1. I substitute my 8, and then I get my 1/9. So there's my limit, and this is how a limit problem with continuity could look as an FRQ. All right, so that kind of sums up part 3 of this lesson 4.